Thanks, Cheng, for introducing me. Okay, so this talk is about locally decodable codes. The topic is exponential lower bounds for locally decodable codes and correctable codes for insertions and deletions. This is a joint work. This is based on joint work with Jeremiah Blocky, Alina Grigorescu, Xinli Yuzheng, and Mingshen Zhu. Okay. So the outline of this talk will firstly introduce some background for this problem, some motivations, and some definitions. So then we will introduce our results, and then we will see some technical highlights, and after that we will see some open problems and a small summary. Okay, first let's see the backgrounds. So insertion deletions versus Hamming distance. These two are very famous measures for string. So insertion deletion distance is also called additive distance. Consider two strings x and y. The additive distance, insertion deletion distance, is a minimum number of insertions deletions transforming x to y. For example, for this picture, if we want to transform x to y, then we only need to delete the second bit and then insert another bit. So the insertion deletions, the number of insertion deletions is 2. Notice that there are several different definitions. For example, some definition for additive distance will include the operations of substitutions. But here we only consider insertions and deletions. Okay, for the Hamming distance case, so the definition is very classic. So for two strings x and y, the Hamming distance is defined to be the minimum number of substitutions transforming x to y. Okay, then we introduce our major object we studied in this talk, which is error correcting code. So the error correcting code is basically a function. This function is mapping a message set to a code word set. Consider this message set to be this capital M. Usually, we consider it as a linear space. And in this talk, we will only consider the binary case. So this is a n-dimensional binary space. And the code word set is a subset of another linear space, usually. So here the W, which is all of the code words, the subset of n-dimensional binary space. The code is defined to be the C, which include all the strings in this capital W. And usually the encoding is formalized as a function, which is this ENC function. Okay, the distance of C is small d, which is the minimum of all y, minimum of the distance over all yz in C. So for different distance measures, we can define different distance of this code. So this distance measure delta can be insertion deletion distance or Hamming distance. Another important important parameter is the information rate, rho, which is defined to be m over n. And the next important parameter is this distance ratio, delta, which is defined to be d over n. So intuitively, we want to construct the codes with high information rate and high distance ratio. Okay, unit decoding. So it is called error correcting code because it can correct errors. And the decoding procedure is a procedure of correcting errors. So a decoder with radius ratio eta for C is an algorithm DEC such that for every X, which is a message, and for every Y, which may be a corrupted code word, such that if the distance between C and this C of X and Y is less than eta n, then it holds that the decoding function can get X when the input is Y. In this picture, we can see that usually it is used in such kind of scenarios in networks. So Alice has a message which she wants to send to Bob. However, the channel is noisy. there can be 8n errors, maybe insertion, deletion errors, or maybe Hamming errors. So Alice has to somehow encode its message. And this message C of X, this message is encoded to be C of X, which can be resilient to these errors. So after these errors, it becomes Y. However, because it can be resilient to these errors, so Bob can use this DEC function to get back X.
So question, what do you mean by error?
Errors. Okay, so there are two different kinds of errors we considered in this talk. So first is Hamming errors. Hamming errors is just substitutions. For example, you substitute some binary bits by another binary bit. So for example, replace 0 by 1 or 1 by 0. The second kind of errors is insertion deletion errors. So insertion deletion errors is just that you delete something from the string or you insert some symbols into the string. Notice that this kind of errors can cause the string length to change, which is more hard to handle. So this kind of errors is even harder to handle.
Can I have a follow-up question? Is there any other type of errors that maybe you can consider for a unique decoding?
Yes. So of course there are many other kinds of errors. So for example, there are some generalization of insertion deletion errors, like block insertion or block deletions, or some block transformations. So this kind of generalizations. And I believe there are some other different kinds of errors. So in general, it can be any functions over this string, right? So we just have some limits on this function. So this function can, on input of the code word C of X, the function can basically do anything on this code word and then give another string which is corrupted. But however, if the function has some very strong ability that he just totally changes the string, then there's no useful information left. So that's too strong. So we have to have some restrictions. For example, it can only visit bounded number of positions, and it can only change a bounded number of positions, or some other restriction, like for example, the computation power of this function is limited, or something like this.
I see. Thanks.
Okay, sure. Good questions. Okay. A related definition for decoding is this local decoding notion. So consider we have a message X, and we again have a encoding of X, which is Y. And there are some errors applying on this string. For example, insertion deletion errors or Hamming errors. Now consider we want some stronger notion of decoding in the following sense. So the decoding the decoder want to compute some bit of X, for example, just one bit of X, which is Xi. However, we require that the decoding can only use Q queries, which means that he can only query Q bits from Y prime, and only use this Q queries to compute this Xi. So this seems to be a bit difficult because for example, consider this Q to be some constant. The number of bits the decoder can visit is pretty small. So the information he can get is pretty small. How can he recover this Xi? Okay, so concretely, we give the local decoding definition as the following. So first we start from the Hamming case. So in this definition, let's say we say C is a Q eta epsilon locally decodable code if there is a probabilistic algorithm DEC with the following properties. For every X, every X, which is a message, for every Y, which is a corrupted code word. However, with distance D of C, X, and Y being at most 8n, then we want to make sure that for every I, we can have that the probability of decode the DEC of y and I, which is equal to xi, is at least half plus epsilon. That means that first given this decoder index for the message, and then we can make sure that no matter which I is given, on reading some part of this y, this decoder can get the correct xi with some significant advantage comparing to random guess. So we require that the decoder can only mix at most q queries to y. Okay. Actually, for this classic question, important open question is that given q, eta, epsilon, and m, what is the smallest n one can get? From the past 2 or 3 decades, there are a lot of works studying this question. We will see later what's the current situation for the study for the Hamming case. But let's firstly introduce a similar notion, which is local decoding for insertion deletion distance. So this definition is very similar to the definition in the previous page. However, there are some tiny difference. So first, we see this is a insertion deletion locally decodable code because we are considering the errors to be insertion and deletions. So we can see that here for every x, which is the message, and for every y, which is a corrupted string, corrupted code word, we require that the insertion deletion distance between c of x and y to be at most eta times 2n. Notice that the right letters are the difference. So insertion deletions can cause the string to change its length. So we don't have a specific loss requirement for this y. And also here, the number of insertion deletions is required to be at most eta times 2n instead of eta n. So this is because insertion deletions are usually called half errors. So consider the string of all 0 and consider the string of all 1. We can see if they all have length n, then the Hamming distance is just n. However, the insertion deletion distance between these two strings are actually 2n. So that's why we have this 2 here. Okay, so that's all of the difference. Other things are the same. And of course, we will have the same question. So given q, eta, epsilon, m, what is the smallest n one can get? Okay. But before considering this local decoding question, let's first see the previous work on Insdel codes. Because if we want to have a locally decodable code, then it has to be a code. So let's see what kind of Insdel codes we already know from previous works. So this study was initiated by Livingston in the 1960s. So he showed some existential result for this for this question, some existence of insertion deletion codes. And the first efficient construction is given by Schwerman and Duckman in 1999. And lately, there are some improvements in the high noise and high rate regimes. Then recently, there are a lot of works come out. So first is a sequence of works about synchronization strings. This kind of objects is very useful in constructing Insdel codes. Basically, one can show there can be explicit construction of such kind of strings, such that we only need to use a error correcting code for Hamming distance, and then do a symbol-wise concatenation with this synchronization string. And then it turns out the resulting code is actually a good Insdel code. That's an amazing result. Firstly initiated by Hubler and Sharsby. And literally, some of our works figure out we can have another kinds of constructions for the binary case. And for binary case, we cannot use synchronization strings. And there are also some other works recently which is considering the linear version of insertion deletion codes. Okay, let's go back to our topic for Insdel locally decodable codes. However, the construction is pretty limited. Although there are some very recent works, however, the most useful construction is to just attach index to the code word symbols. And then by using this technique, we can somehow establish a reduction from Insdel codes to Insdel locally decodable codes to Hamming LDCs. And then we will use this index to somehow simulate the decoding of the Hamming LDC. That's a major idea of this kind of construction. Okay. Then let's see some previous results on Hamming LDCs. So this is for answering the major question we mentioned in the definition page. Notice that the following results are known for Q, eta, epsilon LDCs, where eta is a constant and epsilon is also some other constant. So for the Q equal to 2 case, the famous upper bound is a very classic construction, which is hardware code, such that the code word length is 2 to m. And the lower bound is very close to the upper bound. It is shown by some previous works that the lower bound is exponential in m. This lower bound is shown by Krenidis and Worf in 2004, and also by Ben Arroyo et al. In 2008. For Q, which is equal to at least 3, we have this exponential upper bound, which is some explicit constructions. These constructions are given by Yakani 08 and by De Veer et al. 2011, and also by Afremenko 2012. However, there's a big gap in this situation. That is, we cannot show a very strong lower bound for this case. The best lower bound we can get is by Woodruff 2007, which is just slightly above linear. You can see this is a truly large gap. The upper bound is something close to exponential, but lower bound is just beyond linear. Actually, this is a major battleground for this line of study, how to construct some constant query locally decodable code for the Hamming distance case with some information, some code word lengths much less than exponential, but for example, can be polynomial. The next situation is for the polylog query case. We know the read-Muller code is a very classic construction in this case. However, there's no known lower bounds except some trivial lower bound, which is something like omega of m, because you have to you have to have all the information of the message, so it has to be omega of m. And also for more queries like polynomial number of queries, the upper bound is also given. The upper bound is actually very good, which is the big O of m. This work is by Kopati et al. In 2017. However, the lower bound is still not known, except the trivial one, which is omega of m. Okay,
sorry.
Yeah.
Yeah, sorry. What does regime means here?
Sorry.
What does regime means here? The left column.
Regime. Okay, so this just means different regime for different number of queries. It's just
I see. It's just qualify the second column, if I understand correctly.
Yeah, right.
Okay, got it. Thank you.
Okay, sure. Okay, let's see our results. Our results are about insertion deletion locally decodable codes. So we first have the insight, the observation that actually all the lower bounds for Hamming LDC will hold for Insdel LDC, because Insdel LDC can also be Hamming LDC. So we do need some stronger things to be in order to be meaningful. And actually, we indeed found something stronger. So let's look at the difference. So for the constant query case, so for Q equal to 2, actually there's no upper bound known, which means that there's even no explicit construction. There's no explicit construction, and there are even no existential constructions. And however, we showed that the lower bound is actually very strong. So for nonlinear case, we showed that the lower bound can be exp of m, which is similar to the Hamming distance case. However, for the linear case, we show that this is infinity. In other words, we showed that no matter how long is the code word, we can only have constant number of message bits. That's pretty strong. That's much stronger than the Hamming distance case. And for Q, which is at least 3, we still don't know any upper bound for insertion deletion LDCs. We know some upper bounds for Hamming LDCs, however, they cannot be used for the Insdel case. And also, we have a stronger lower bound for Insdel LDCs than Hamming LDCs. Our lower bound, we can see, is close to exponential. For the polylog case, when Q is at most this log m over 2d times log m, we again show some quasi-polynomial strong lower bound, which is something like exp of log m to the power of d minus 2. However, there's still no known upper bound for this case. The only upper bound we can have is by the very recent work from Ostrowski et al. And Block et al., which gives a which is comparing Hamming LDC to Insdel LDC, given the upper bound of codeword length m to the power of 1 plus 1 over d minus 1 plus o small o of 1. For sub polynomial case, when the query is something like m to the small o of 1, we again have this upper bound big O of m. And however, we don't know any strong lower bound for this case. Okay. So specifically, in the following of this talk, we will focus on these two theorems. So the first one is that for any non-adaptive Q eta epsilon Insdel LDC with Q which is at least 3, we will have this kind of lower bound, which is close to exponential. And specifically, I mean, for the linear case, for the linear 2 query case, we will have the next important result, which is saying for any linear 2 eta epsilon Insdel LDC, we can only afford constant message length. Okay. Next, we introduce some technical highlights. So let's briefly, in a very high level, review the previous strategies for Hamming LDC lower bounds. So essentially, all such proofs begin by observing that the code needs to be smooth. So here, smooth means that for any target message bit, the decoder cannot query a specific index with a very high probability. We can look at the following picture. So intuitively, if the decoder only queries some small area with high probability, then we know this is not possible, because the corruptions, the adversary can just corrupt this small area, and the decoder get no useful information. So intuitively, the query has to be spread out. He has to. I mean, the support of the random queries should be everywhere. Yeah, that's a high level sense. And if this is the case, if the code has some smooth decoding properties, then this implies that every message bit has a large amount of code word bits correlated with it. In the very extreme case, you can think that the correlation is roughly close to 1. And that means that, so if you look at this red message bit, then look at all the pointers, the red pointers. If these pointed bits are all have some correlation close to 1 with this red bit, then we know that they are also fixed by fixing this red message bit. However, the message bits are independent, so we cannot afford too many message bits. So that's a very high level idea. However, all the previous works, all the previous proofs, they are considering Hamming distance case. For the Insdel distance case, if we want to get something stronger, then we need some new techniques. And our proof is different, significantly different from previous methods. We're using the following ways. So our proof can be divided into the following 3 components. So we first develop a random deletion process with certain concentration and anti-concentration properties. Then we show that the error distribution induces some strong smoothness property. Then we wrap up the proof using some type of entropy arguments. However, the smooth property we defined and the entropy arguments we used is significantly different from previous ones. Okay, let's see what are the important points in this proof. So first, we will introduce the error distribution. So the high-level idea is that we will use this error distribution to argue some kind of smooth property of the Insdel LDC, which means that given me the Insdel LDC, as long as it can correct, it can do decoding for a constant fraction of insertions and deletions, then we can we know that we can develop some error distribution which can be corrected by this decoder. And then we will argue that as long as it can handle this kind of error distribution, it should have some very good smooth properties. So this distribution is defined as the following. So we first, it has 2 steps. So first step, we pick a real number beta, which is in this small range. Recall that eta here is a fraction of errors which can be corrected by the local decoder. So beta is in the range from eta of 8 to eta of 4. That's a pretty small range. We'll pick this beta uniformly at random. And then this, we will then delete each bit in this code word independently with probability beta. And the next step is that we will pick an integer r. This r is from uniformly in the range 0, 1 to roughly eta m over 4. And then we will delete the first r bits. And that's an error distribution. So we will denote the set of deleted bits as d. We can say d is such a random variable defined by this error distribution. And why this distribution is useful? Let's see, what kind of properties can we get from this kind of distribution? So this distribution is specifically used for 2 query cases. So consider a pair of queries, a pair of indices, k plus d, where k and k plus d are both in n. So let's see the decoding procedure. So the decoder want to see that the decoder want to query k plus d. However, there are some random deletions applying to the code word. So actually, he's querying k prime plus d prime. Okay, we can have the following observations about d prime. Notice that this d prime is derived from our error distribution, where we think of the situation that we apply this random deletion procedure to the code word. Firstly, the conservation property. We can argue that d prime is in the range d from D to 10D with probably at least 1 minus epsilon. Recall that in the random deletion process, we first randomly pick this beta. However, this beta is only in a very small range, so there are only a small number of bits being deleted. So then we can see that by a simple concentration bond, we can show that this D prime is in this range D to 10D. The second property is the anti-concentration property, which means that for every G in this range from D to 10D, the probability that D prime is equal to this G is upper bounded. This is very important in our proof. But why this is the case? This is because recall the deletion process. Actually, we only need to recall the first part of the deletion process. It's a random deletion in the sense that we first randomly pick this beta, right? And this beta is actually, if we fix this beta, we do not randomly pick it. We just fix it. Then we know that the number of bits deleted is roughly close to Gaussian distribution. However, if we randomly pick this beta, then actually we are randomly picking the expectation of this Gaussian distribution. And if we randomly pick this beta in a range, then we can look at this picture. We can think of this whole distribution as a convex combination of several Gaussian distributions. And the difference between these Gaussian distributions is only their expectation. And in a very intuitive way, you can see that if we pick beta in that range, then the whole distribution will somewhat be like uniform in a certain range. So that's a intuitive idea of showing this anti-concentration model. We also delete the first R bits for random R, and that is for this that is for this K prime. Notice that if we randomly pick this R, then this K can be K prime in a big range. So overall, we have that for every G1, G2 in this n times n space, the probability that K prime plus D prime is equal to this G1, G2 is at most big O 1 over ND. So intuitively, we can see that after this random deletion procedure, we are considering two queries. And the first query is this K prime, which is like uniform within a large range. And also, the second query is also looks like uniform over another large range. Okay, we can derive some host property for the queries. Actually, we can, in general, derive some smooth property for more queries by generalizing the previous error distribution and the previous analysis. Actually, for more queries, we can have the following smoothness lemma. For any G1 to GQ, we can have that the probability that this Q queries, which is equal to a specific Q tuple, this probability is at most a big O, some polylog m over m times d1 to dq minus 1. But we can only consider the two queries because we will mainly see the technique for two queries. So after establishing this kind of smoothness, we can define the correlation with the message. That is the definition of the good set. For each I, we can define the good I to be the set of queries big Q such that there exists F, such that when we apply this F on this Q bits of the codeword C, we can recover Xi with high probability. Once we have this definition, we will immediately have the following two lemmas. So each Q is good for most big Q different I's. That is because a simple entropy argument. The second property is the hating lemma, which says that this decoding must hit good I with probability at least 3 epsilon over 2, because we already require the decoding function to have some advantage, like half plus epsilon. So this means that it has to hit this good I with a certain probability. Okay, then in particular for some fixed query k plus d in the support of the decoding procedure, we can show that the probability that after random deletion, this k prime plus d prime is still in this good I has to happen with probably at least 3 epsilon over 2 on our error distribution. We think that such a query is good for I. And the final step is to wrap up the proof. We use a entropy type argument. So we first partition the query space 2n times 2n, the first 2n for the first query, second 2n for the second query. And then we define the following notion PG, and we use the different PG to partition space. For G, which is in the range at least 1 to at most T, we denote the PG to be 2n times range from 10 to G minus 1 to 10 to G. Then we consider we fix k plus d, which is good for I. Let G be such that this d is at least 10 to G minus 1 and less than 10 to G. Notice that this 10 powers are just a geometric sequence. So definitely we can have d in some part of the sequence. So by concentration property, we can show that k prime plus d prime is in PG union PG plus 1 with probability at least 1 minus epsilon. This is because the concentration property. Recall that the concentration property is saying that d prime is in this range with high probability. So of course we can have this. Then we can use the Hating lemma, which implies that this k prime plus d prime is in this good I intersecting this PG union PG plus 1 with a small probability, but small, but which is still a constant. So this is because recall we have the Hating lemma, which is showing that this decoding procedure must hit its good I with probability at least 3 epsilon over 2. So with a simple union bound, we will see this inequality. The above event will happen with probability epsilon over 2. The next step is to use a smoothness lemma. We know that. So in the previous page, we showed that the decoding will hit this set good I intersecting PG union PG plus 1 with constant probability, right? And recall our smoothness lemma, which is showing that so any support G1, any element in the support G1, G2, we can have that k prime plus d prime equal to this element with a very small probability. So then this means that we have to have a lot of elements in this set. So we can derive that the set actually has sets at least omega and d. And that is exactly the key point in our proof. A few more. We can show that we only need to consider one of the PGs. So there exists one of them in G and G plus 1. We can show that this set good I intersecting PG prime has a large size.
Sorry, you're running out of time.
Yeah. Okay. So actually, we reached the end of our proof. By using this inequality, we can establish. We can bound this summation from the two sides. From the right-hand side, we know that by the above inequality, we can directly see that this is at least a theta m. However, from left-hand side, we can show that this is at most big of log n, because the inner part is big of 1, since each Q should be good for only a constant number of masterpieces. Then that's a proof. This proof can be easily generated to generalized to more queries. Okay. Thanks for listening.